Yeah, hi, Shobik.
Hi. Good evening. So, welcome to this live session. We will be solving assignment 5 today. Uh, Lakshman, were you able to clarify the doubt regarding the calculator?
No, that I have sent the email, but I did not get any response. So I'm planning to send another reminder mail by today or tomorrow.
Okay, fine.
If you can, if you or at your level, if you can talk with the next level of management and help on that one, because something would be decided, right? I just want the decision. What is the they're going to consider it or they're not? They are not going to consider it. If definitely they are not going to consider means again it's going to be common for everybody. Okay, I will accept. We are accepting it. But what I think is it is in engineering examinations the calculators are allowed. Why here it is not allowed? That is the thing. And moreover, I'm just learning it. I do not have any big objective for becoming or writing a big gate examination or other things. This is just for learning purpose for me. So if I have a calculator means I'll approach it in a different way and try to do that one.
Okay, fine. I will talk to the NPTEL team. I'll drop a mail to them. Let's see.
Yes. Okay, and in your last session when I was
Yeah.
checking the manual, I mean your solutions thing, I noted
Uh,
one thing. uh, it was in one of the problem it was mentioned as the motor current as 1.25 per unit, I guess. For that problem what happened is we have not considered that
hmm.
1.25 per unit in the calculation. So that
Okay.
has to be considered in the calculation, I guess, because otherwise the output is or the derivation is not working properly. Anyway, that also I
Uh,
have given email in that thing. It's not related to this PDF. The same thing has been done by another session, right? Sunday another LED condenser session,
uh,
there
yeah,
also I
yeah.
have noted the same thing. So I have I just marked that thing and given an email, and then I got a reply from the NPTEL team that yes, it should be considered in the calculation like that.
Okay. So which problem it was?
Question number 7, I guess.
Question number 7. Acha. Okay,
Yes.
I'll check.
Yeah,
I'll check.
okay then.
Okay.
Yeah, we can start the session then.
Yeah.
Yes.
So you can see my screen, right?
Yes.
Okay. Assignment 5 is regarding transmission line. If you have done network theory well, in that there is a chapter called two port networks. In there, there are number of parameters there, like Z parameter, Y parameter. Then one of it is ABCD parameters. So ABCD parameters are mainly used for transmission uh, line problems mainly. So this is heavily linked with this kind of problems, transmission lines mainly, and we will be doing this. And the problems here are very pretty simple as compared to last week. There is no complexity as such. Only the thing is that we have to be a bit careful regarding the calculations. And we will try to wrap up this assignment today as quick as possible because the problems are also on the shorter side in terms of length. So let us solve the first one. It is saying ki the ANC parameters of a three-phase 220 kV rated voltage medium transmission line is represented by ABCD parameters, and these are given A and C. So what would be the B parameter of the line? Now, if you have studied the ABCD parameters, you will see that there is a this thing. What you say? Um okay. So there is a small kind of a formula for that. AD minus BC equals to 1, and you will get a proof for this also in the textbooks. And we also know that A equals to D. So which is this thing, your 0.8749 at an angle of 1.2. So if you substitute the values in this formula, you'll directly get the value of B, which is, and just keep a note of the angles also. So if you calculate this, you will get a value of 191.486 at an angle of 80.417 degrees, which is your option B. So this is pretty straightforward problem. You just have to know that there minus BC equals to 1 and your A equals to D. Using this, you can calculate B. So this was for problem 1. I hope this was clear. Pretty
Yes,
simple.
it is clear. I have a
Yeah,
question. It's just not related to this question alone. I have
yeah.
seen one or two problems in the lecture session also. Here in the question, it is marked as 220 kV rated voltage. So
Huh.
here we can leave this ABCD parameters totally. But how should I
Okay.
consider that 220 kV rated voltage? Do I need to consider that as a sending end voltage or receiving end voltage? If
No,
generally it is mentioned in the question, because there were questions in the assignments also and in the problem solving session also, I have found it in some questions they are mentioning like you need to find the sending end voltage, so then I am taking this as a receiving end voltage. In another problem they are mentioning you find the receiving end voltage, then I'm considering this as sending end voltage. But what this 220
I
kV
get
rated
your
voltage
problem.
should be
So
rated?
see, uh, in some questions where you are saying you have to calculate the sending end voltage, in that case they are mentioning the what is the power being drawn at the receiving end and what is the power factor and also the receiving end voltage. So there you calculate what is the current flowing through this transmission line, right? And there is a voltage drop there. Using that V plus IZ, you calculate the sending end voltage. But normally for transmission lines, there is a so at the sending end there is a transformer, right, which steps up the voltage, let's say from 25 kV to let's say this 220 kV, and then at the receiving end there is again a step down transformer which step downs it the voltage from 220 to let's say 33 or 11. So generally this is considered as the, from what I understand, this 220 is considered as the voltage of the transmission line only, unless and until it is something other is specified.
Okay, let's go to the next upcoming problems. I think we will come across the same case again. Let's
Yeah,
see.
yeah, yeah.
Okay.
So next problem is only that, if you see. So it says that a three-phase 50 hertz 20 kilometer line, long line delivers 3 megawatt at 11 kV 0.8 power factor lagging. So when it says this, you immediately understand that the receiving end voltage is 11 kV and now line loss is equal to 10% of the power delivered, which is this line loss means the I square R loss mainly. And line inductance is 0.9156 milli Henry per phase per kilometer. What is the sending end voltage of the line? So here you have the inductance which is per phase per kilometer. You calculate it in per phase, so it comes out to be 0.9156 into 20. It comes out to be 18.312 millihenry per sorry, per phase. Now you calculate the inductive reactance 2 pi fl. It comes out to be 5.73. Now the per phase receiving end voltage or the load voltage is 11 root 3 kV. Your power being required at the load is 3 megawatt. So the current that would be flowing through the transmission line is your load by voltage and the power factor. It comes out to be 196.824. Then line loss, they have said it is 10% of this 3 megawatt power being delivered. When you do it, it comes out to be zero point 0.3 megawatt. So the per phase resistance of the line is this power divided by 3 times I squared. So 3 because this is per phase current, and we have to multiply it with 3 because it's actually 3 I squared R. So you calculate, it comes out to be 2.58 ohms. So your Z per phase would be 2.58 plus J 5.73. Now you could simply calculate the sending end voltage. so this is the receiving end voltage per phase, and you multiply it with the I mean it would be added to the voltage drop across the line. Now one thing you just have to remain careful is that sometimes what we do, we miss this term, zero point 0.8 minus j zero point 0.6. This is the power factor of the receiving end, basically the current, right? Because voltage is at an angle of 0, so we have to add it to the current only, this term. So and it is multiplied with the uh, inductive, I mean resistance plus reactance. So when you do that, it comes out to be the magnitude, it comes out to be 7.46. Sorry, this will be volt. I'm sorry, I will correct this. And so the this is the per phase, so the line voltage would be root 3 times of this, which is 12.92 kV, which is your option C. So I hope this was clear.
Yeah, yes.
Yeah. So, Lakshman, what you were telling, I mean, did you understand what I said in the previous problem, and what that voltage car thing,
I-
transmission
i-
line?
Here it is clear. We'll go
Yeah.
through the other problems and see it, because
Okay.
there, one question I saw, the load is not mentioned. Example, it was similar to the previous question where the load is not mentioned,
Okay.
and
Fine.
it was something different. Let's see if that kind of problem exists in the
Okay. Okay.
coming
Fine.
part. Yeah, okay, it's clear. This problem is clear. Thanks.
Okay. So next question is the ABCD parameters for a 100 kV transmission lines are given below. If the receiving end voltage is 110 kV line to line, find the magnitude of no load charging current of the line. So no load charging current means we have a so when we consider this capacity, transmission line, we have a line to ground capacitance, as we saw while solving the capacitance, the GMD GMR of those problems in probably assignment 3, as far as I remember. So we saw that there is a line to neutral capacitance. So due to this, a current flows from the line to the ground. That is nothing but the no load charging current. And this is equal to, if you see the formula, um, mainly for short and medium transmission lines, it is given as C times the receiving end voltage. So, I mean, if you use any type of T parameter, just leave it. You don't have to consider that. So, it is just C times VR. So, C is nothing but, if you see the units, it's nothing but ohm inverse, right? Siemens. So, J times 0.0054 Siemens. Now, if you calculate, it comes out to be 34.295 ampere. So this is a pretty simple problem, provided you know this formula. I charging current is C times VR. Yeah, this is for problem 3. I hope this was clear.
Yes.
Yeah. Now next problem is also very simple. It says that a 132 kV 100 kilometer long three phase, this transmission line has all of these ABCD parameters as mentioned above. The line is energized with a balanced three-phase 132 kV voltage at the sending end when the receiving end voltage is negligible. Find out the approximate percent change in the receiving end voltage from its nominal value due to the Ferranti effect. Now we know what is Ferranti effect, right? Basically, during light load or no load conditions, what happens is that the receiving end voltage is slightly greater than the sending end voltage. So that is basically Ferranti effect, and there are some proofs also regarding this, how the receiving end voltage is greater than sending end. You may consider see any textbooks or the lecture sessions as well for that. So Now we know this to solve. Now we are solving the problem. So we know this, that Vs is A into Vr plus B into IR, the ABCD parameter, the first equation. Now since IR is 0, so this whole term will be 0 and your Vs would be A into Vr. Now if we consider, so we have to calculate per phase only, or it is not required, you can do that in line values also, since you just have to find out the percentage change, right? So Vs, it is clearly said that the line is energized with three phase 132 kV voltage at the sending end. Therefore, sending end voltage becomes your 132 kV. And the A parameter is also given. You just divide this, you get this thing 83.842. This is the per phase value. And if you calculate the difference, it comes out to be 10.014. Now denominator should be having the sending end, because we are calculating the change, how much the receiving end voltage change with respect to the sending end voltage, right? So that is why the denominator must have the sending end voltage term. So it comes out to be option C, 10.014%. I hope this was clear.
Yeah, yes.
Now, question number 5. So, a three-phase transmission line has the following data: resistance of each conductor. So, resistance of each conductor means each phase basically, and inductive reactance of each conductor also is 40 ohm, and susceptive, see this term, susceptance to neutral is 0.0004. So basically the line to neutral, sorry, line to ground capacitance basically, or neutral capacitance, whatever you may call it, is 0.0004 ohm inverse, and load at the receiving end is 12.5 MVA, and so voltage at the receiving end is 66 kV. So determine the A parameter using the pi model. So just for your convenience, I have drawn this diagram, and all of these parameters are given. So A is basically 1 plus yz by 2. I'm sorry for this, this will be slightly up. Anyways, so when you just replace all these terms, so z would be 20 plus j40, and if you do this, it comes out to be 0.992 plus j. Sorry, this will be what, 0.004. So it slightly lifted up. I'll correct this. Which is your option number D. This was again pretty simple. So I hope this was clear. So let us go to problem number 6. It is the same problem. It is just saying ki determine the percentage change in the regulation of the line using pi model. So again the same, we just have to calculate here the sending end voltage and find out the percentage regulation of the line. So now we have to calculate what is the we have been given all the um, uh, parameters at the receiving end side. So I have made a mistake here. The load would be 12.5 into 0.8, right? So anyways, I will correct this. So and here there won't be any power factor, right? We just have to since this is 12.5 MVA, and this would be MVA only. So I per phase would be MVA divided by the per phase voltage, right? There won't be any power factor. So it comes
But
out,
it is mentioned in 12.5 MVA at point 0.8 PFA. The question it is mentioned, right?
yeah. So see, if you multiply the MVA with the power factor, you get what, the megawatt, right?
Megawatt.
MVA
Okay.
into, so that is why you don't need this 0.8 while doing this,
Okay.
right?
Okay.
So MVA is yeah, what, yeah, MVA is the um, hypotenuse of the triangle, and megawatt is the base of the triangle, right? So cos of that becomes cos of MVA becomes megawatt. So that is why you don't need this 0.8. Yeah, anyway, so I hope that this current value is all right, because I was getting the correct option. Anyways, I'll check again, but you see the process. So we are getting the per phase receiving end current. Now we know कि Vs equals to AVR plus BIR. So for this pi model, B equals to Z. The B parameter is equals to Z. So 20 plus J40. Now we calculated what is the A in the last question, which was this, and it is equal to D only. And so yeah, you don't require C here. C would be requiring in the next question. So when you substitute all these parameters, you get 42.2313 kV, and the percentage voltage regulation is the sending end minus receiving end voltage divided by the receiving end voltage. So sometimes what happens is that we use the sending end as the denominator, which is not right. So voltage regulation is calculated with respect to the receiving end voltage. So when you do this, it comes out to be 10.83 percentage, which is what option number A. So I'll check with the value whether I have written it correctly here, and I'll post the right PDF of this, modified PDF of this. So now, so this was a pretty simple problem, I hope. Now, when we come to the next question, it is telling ki determine the sending and power factor, right? The other things are same, but it is the question is determine the sending and power factor. So in the last problem, we saw that the sending end voltage was coming out to be this, right? The magnitude is this fine, but it has a certain angle. So when we for sending end voltage, when we calculate it, it comes out to be 42.213 at an angle of 2.988 degrees kilovolt. Now considering the current, so it is Is equals to CVR plus DIR, right? So we previously saw that A equals to D, and your C would be Y into 1 plus YZ by 4. Now when you calculate all of this, it comes out to be this thing. So you have to be pretty careful using this, because you see that 0.0004 into these are very small formulas, right? You tend to ignore this. Initially I ignored this and I wasn't getting the answer. So you can't ignore this, because clearly you see that when you multiply this term 8 into 10 to the power minus 7 with this voltage, it comes out to be a pretty big term. So I mean, in some point 0.0 or something, so it will affect your calculation. So you can't ignore this small term. So when you put this C value and D value in this thing, you get a value of 100.12 at a angle of minus 29.66. So sending end power would be what? The cos of the angle of the sending end voltage minus the angle of the sending end current. So the angle of sending end voltage was 2.988, and it was for current it was 29.66. So this minus minus becomes plus, and you get 0.842. So just be careful using this, because generally when we calculate the power factor, we just simply take the cos of this current angle, right? We do that only when the voltage has a I mean, it is a pure what you say pure term, right? It doesn't have any J term there. But if you see the voltage, it is not an angle of zero, which means that it is having some J term, imaginary term. So that is why this formula you have to use while calculating the sending end power factor. So if you do this, it comes out to be option number B, 0.842. So lag because it is minus, right? this thing is minus. So yeah, I hope this was clear.
Yes.
Yeah. Now we will go to question number 9 directly. So question number 8 is for you to solve. I'll come to this. It's at the end. So it is saying here three phase 460 50 hertz transmission line is 475 kilometer. Now looking at this distance only, you can feel that, you can get a feeling that this is long transmission line, right? Because short transmission line is still, I guess, 80 or 100, and uh, medium transmission line is probably what, 180 or 200 kilometers. From then onwards, it's long transmission line, and it is assumed to be lossless. So the line is energized with 460 kV at the sending end when the receiving end load is removed. So you see that the line is energized with 460 kV at the end, right? So immediately you get that the sending end voltage is this. When the receiving end load is removed, the sending end current per phase is this, J 546.6 amperes. If the phase constant in radians per kilometer is given as 0.0015 radian per kilometer, determine the voltage at this condition, right? So it is again the same. We know that Vs equals to AVR plus V into IR. IR is 0. So you use this equation, but you have to calculate A, right? So now for long transmission line, there is a separate. These are mainly distributed parameters, right? For short and medium transmission lines, we use lumped parameters, lumped model of resistance, inductance, and capacitance. But distribute for long uh, transmission line, we use a distributed parameter. So we consider a very short section of the transmission line, and we use that model for the whole line. So there is a separate derivation, everything for that. Now if you see that derivation, you will get that the a term is coming out to be cos of gamma l. So gamma l is mainly the propagation constant, which is equals to alpha plus j beta, and alpha is the attenuation constant. Now in this question, and beta is the phase constant, obviously. So if you see this question, there is no information regarding alpha, right? So we have to take it as 0 only. So alpha plus j beta. So only beta is there, and j you can ignore since alpha is 0. So it comes out to be beta L. Now there is one thing in this calculation, beta L. So this is given in radian, right? You have to convert it into degrees. For this problem, so degrees is mainly, you do this 180 by pi, right? You just simply substitute 180 by pi multiplied by this radian. Now if you consider 180 by pi here, this angle is coming out to be what, 38 point, I mean, if you round up, it comes out to be 39. And if you use 39, you won't get this value, because cos of 39 and cos of 40.82 would make a world of difference. So that is why, I mean, I tried to, recheck and recalculate, and I found that you, for solving this assignment, you have to take the value of 180 by pi as 57.29 only. So that is why, if you calculate this, it comes out to be 40.81 something. You round it off to 40.82, and when you substitute this, it comes out to be 607.85, which is your option number D. Otherwise, you would be getting somewhere between 590 to 600, and there is no option in this ABCD. So that is why you have to use this for your calculation. And you please be careful while solving the assignments also. Just be careful. So I hope this was clear.
Yes.
Yeah. Now this is also a very similar problem. So again the same thing, everything is same. So if phase constant beta is in radian per kilometer is given, find out the surge impedance. So surge impedance we know that is ZC, which is given by root over L by C. Anyways, we only need to know the ZC. So again we use the second equation, Is equals to CVR plus DIR. Again IR is 0, so VR is Is by C, right? We know VR, we calculated in the previous problem, and C is sine beta L by ZC. Okay, so now you calculate again, you have calculated the beta L, and we know every parameter here, right? We know Is, we know VR, and we know beta L, which is 40.82. You calculate this, it comes out to be 419.705 amperes. So this is your sorry, I have to check this. This is not matching, right? Anyways, I will get back with this problem. I'll try to post the right solution. So this was coming out to be 419.75 only. So I will get back with this problem. I'll post the right solution here. But anyways, the process is this. I'll try to check with the answer. Now, if you come to problem number 8, so it's a different problem and I've left for you to solve, but I've shown the steps here. So it is saying here 3-phase 60 hertz. Just make sure this is not 50, this is 60. So 60 hertz 460 kilovolt transmission line is 450 kilometer long. The line inductance is this, 0.4 millihenry per kilometer per phase, and capacitance is 1 nanofarad per kilometer per phase. Assuming the line to be lossless, if the receiving end load is 200 megawatt, 0.75 power factor leading at 460 kilovolt, determine the sending end reactive power. So you have the VR, you can calculate the IR from this thing. You calculate their phase values. Now we just have to simply use these two things. So and we know every this term, so A equals to D, so cos beta L, and you have to be careful, you have to use this J term, gamma, right? So as I told, gamma is the propagation constant, so gamma equals to alpha plus J beta, right? So your alpha is 0 and the J comes outside. So J beta L, so J comes outside. So that is why for this sine term you have this J here. And anyways, these are the A and D are unitless, right? And J has a this thing. So ZC, that is why you see a J. And this is in ohm and this is in ohm inverse. So you have to incorporate this J while you are calculating, and your finally you're sending in megawatt, which is your reactive power, would be 3 times the sending in voltage and current, right? I mean difference of angle. So if you calculate this, it was coming out to be 193 point some, minus 193 point something, which is your option number C. You can try this. I hope you will get the answer. So this was, I hope this problem was clear.
Yeah, yes.
Yeah. So this is it for to assignment 5. Pretty simple problems. I will post the right answer for this. I'll check again. And yeah. So this was, I guess, all about for today. Uh, so Lakshman, I'll try to see the problem number 7 also of assignment 4, and I'll get back to you. probably in the discussion forum only.
Okay.
Yeah.
And one more doubt I have about the per
Hmm.
unit system.
Yeah.
In per unit system, is it possible to have two different bases for one equipment? I mean, let us consider I'm having a source and load. I'm approaching. Let's consider I'm taking base value from source and approaching towards the source. Sorry, I'm taking the base value at source. I'm approaching towards load. And can I consider a separate base value for base voltage value you can take for load?
No.
Both will
Otherwise,
clash, right? Yeah.
it will clash because you might have some different reactance value, current line current value, and then
Okay.
I mean when you are multiplying it with the base voltage, finally you would get something different, right? So won't be.
Okay. Then if the analysis is done for a very big system,
Hmm.
how they will generally consider in that case?
Big
Like,
system, everything is connected, right? I mean, if you
yeah,
consider a
everything is connected, but I may have a 400 kV, 100 MV system. I may even have 400 kV. At other end, it could be different load level with 1000 megawatt system. And another side, maybe I may have 1200 kV system or 800 kV system.
no problem, na. You can. I mean, if the system rating is very large and you are considering a very small voltage, the base, I mean, the per unit value would be very very small, I suppose, because if you consider the
Mm-hmm.
so no problem in that. If you
Okay.
finally calculate the actual value, you have to multiply it. It would be the same only, right?
Okay.
Yeah. Okay, fine. So we will meet again next week then with
Yeah.
assignment 6. Yeah.
Yes. Thank you.
Okay. Yeah. Bye.
Bye.